XSS, or cross-site scripting.
Cross-site scripting attacks.
With blind cross-site scripting.
In this video, we're going to be talking about cross-site scripting.
Cross-site scripting stands for cross-site scripting.
Cross-site scripting, commonly abbreviated to XSS, is not talked about nearly as much as that introduction would lead you to believe. But maybe it should be. Despite dating back to the 1990s, it remains one of the most prevalent security risks for web applications, commonly finding itself in the OWASP top 10 most critical security risks. If you're even vaguely familiar with web security or penetration testing, you've definitely at least heard of cross-site scripting. But what is it and how does it work? Well, cross-site scripting is an injection-type web vulnerability, where an attacker is able to inject a malicious script, usually JavaScript, into a web page. And then that malicious script is executed by your browser when you load the page. Now that's a pretty high-level, wishy-washy definition. So I think the best thing to do now is to look at an example. So we have a simple web page here that prompts the user for a name. When we hit that submit button, we are redirected to a page that prints welcome and then whatever name we entered. This is what's called reflection. We give an input to the web page and it reflects that input back to us. That word reflection is going to be important later, so remember that. Let's take a closer look at the code for this site. So we have an index.html file that contains the code for the main landing page. There's some CSS, and then we have the HTML for the enter your name card. There's also the submit button that redirects to the /welcome page. Nothing too crazy there. Within the welcome.html file, we have some bare bones HTML. The key point is within the h1 tag. We have the text welcome and then name surrounded by curly brackets. The double curly brackets mark a placeholder, a variable that won't be known until later. When will it be known, you may ask? Well, to answer that, we need to take a closer look at our server file. Here we have the steps that take place when somebody hits the submit button and accesses the /welcome page. The first thing that happens is we read the name query parameter. Hold on a second. What's a query parameter? Well, you've probably seen URLs that look like this. These URLs are separated into sections with identifying characters. You have the protocol used, usually HTTP or HTTPS. You have the domain name or the location of the server you're trying to access. You have the subdirectory or the specific location on the server that you're trying to access. And then occasionally you have something at the end called a query string. The query string will be at the end of the URL, separated by a question mark. The query string will be separated into two parts: the parameter name that acts as a unique identifier for the data, and then the parameter value, which represents the actual data. A query string allows your browser to pass small bits of data to the server. So if we flash back to our example, the query string with your name is passed to the server so it can be inserted into the HTML and then displayed on the /welcome page. So we know that this web page takes our input and inserts it into some HTML and then displays that page back to us. The final key point is that you can insert JavaScript directly into HTML using a script tag. This is a feature of HTML that allows developers to create dynamic websites with one file. The JavaScript in a script tag will be executed the same as any other JavaScript. So with all of this, we can formulate our attack. Since we know our input to this page will be inserted into HTML, and we know we can include a script tag within HTML, what would happen if we included some JavaScript with our input? Well, let's try it. Here we're using the basic alert function that just pops a window up on the screen. And boom, the JavaScript we wrote was executed. Now, you may be thinking to yourself, okay, and? I mean, we're basically attacking ourselves here. We're writing a script and then having our own browser execute it. Cross-site scripters want to attack other people, not themselves, and they can. To do so, we need to take a closer look at the query string. Whatever we enter as our name is appended to the URL as a query string. So if we enter a malicious script, that too will be appended to the query string. So if we craft a URL with our malicious script as the query string, we can then send this link to somebody else and execute the script on their browser. So this is what's referred to as reflected cross-site scripting. We have a client and a server. The client will request some web page from the server, and the server will reply with the requested page. But the page that gets sent has an input form, allowing the client to send some input to the server. The server will receive this input and embed it into a page template. In our example, this was the name variable. Upon receiving this input, the server replies with the web page that has the client's input inserted into it. Cross-site scripters take advantage of this mechanic. Rather than providing a plain text name or whatever input the server is expecting, we provide a malicious script. The script then gets embedded into the web page and sent back. To make this attack work on someone other than ourselves, cross-site scripters go through the process we just outlined and take note of the URL that directs us to the web page with our malicious script embedded. Because our malicious script is stored in the query string, whoever clicks on this link will request a page with our malicious script inside of it. We then send this carefully crafted link to our victim. When clicked, it makes a request from our victim to the server for the page with our malicious script, and the server will reply. This is one of the three main types of cross-site scripting: reflected, which we just looked at, stored or persistent, which we'll look at next, and finally DOM-based, which we'll look at last. Let's move on to a stored cross-site scripting example. The underlying mechanism is the same for both reflected and stored cross-site scripting. It's the delivery mechanism that differs. In this example, we have a simple web page that allows users to make a post. These posts are stored and displayed to all users in the /feed endpoint. The key point is that this page allows users to use HTML tags in their post. For example, we could use a heading tag to create emphasized text. The code in this page is very similar to what we've seen in the last examples. We have a basic HTML landing page for users to make their posts, and we have a server file that handles rendering the /feed endpoint. The server file has an HTML template for the /feed endpoint and has a variable or placeholder that will be filled in with the posts. We then have a load post function that reads in all the posts and inserts them into the template. The posts are stored in a JSON file that the server has access to. So whatever we enter as our post gets stored in this file and then rendered anytime someone accesses the /feed endpoint. You can probably already see where this attack is going. Rather than inserting harmless HTML tags like h1, we'll be inserting a script tag. When we publish this post, it'll get saved in the JSON. Now, anytime someone renders the /feed endpoint, our malicious script will get embedded and run. So rather than hiding our malicious script in a query string like in reflected cross-site scripting, we hide our malicious input in the server's database. This type of attack is particularly dangerous since we don't need to worry about distributing a malicious URL to victims. Anytime anyone visits the /feed endpoint, no matter what URL they clicked on, they will be subjected to our script. The final type of cross-site scripting we'll look at today is DOM-based. Now, DOM stands for Document Object Model, and it's essentially just a tree of objects on the web page showing the hierarchical relationship between everything. Now, don't worry if that doesn't make a ton of sense. It's not super important for what we're going to be doing today. In this example, we have a simple web page that allows us to switch the theme. If you look up at the URL, our selected theme appears after a hashtag. This is what's called a query fragment. It's very similar to a query string in that it holds some value about the user session. The difference is that a fragment stays on the client's end and is never sent to the server. So we can embed a malicious script as a query fragment and run it on the page. In this example, we're using a slightly different payload. Rather than using the traditional script tag as we did in the other examples, we are telling the web page to look for an image that doesn't exist and giving an on-error clause. So when the page can't find the non-existent image, it'll run the on-error clause, which in our case is just another alert function. This is just a different means to the same end, another way of sneaking scripts into inputs. Now, from the surface, DOM-based cross-site scripting looks very similar to reflection-based. An input is given to the web page, and that input is inserted into another page, and that page gets rendered. The key difference between DOM-based and reflection cross-site scripting is where the insertion happens. If you recall from the reflection demonstration, our input gets sent to the server, and then the server embeds our input into a page and sends that page back to us. The server is the one inserting the malicious script. In DOM-based cross-site scripting, the server sends us a web page with logic for inserting new elements in the page. So when we enter our input, it never gets sent to the server. The logic needed to embed it is already sent to us, so it happens right on our own browser. This is why they call it DOM-based, since the logic the server sent us is modifying the DOM on the web page. We can verify this by checking the page's source code. Here we can see what the server actually sent us. In the DOM-based example, we see no mention of the malicious script, meaning the server didn't actually send it to us. But if we look back at our reflected demonstration, we can see that the server is actually the one sending us the malicious script. So, as a quick recap, in reflected cross-site scripting, we send our malicious script to the server, and the server embeds it into another page and sends it back to us. In stored cross-site scripting, the malicious script is stored in the server's database and gets pulled when the page is sent. And in DOM-based cross-site scripting, the logic to modify the DOM is sent to us, and then our browser is the one embedding the malicious script. So far, we've looked at cross-site scripting proof of concepts. We've proved that we can inject and run a script, but the only examples we've seen so far are using the alert function, which is kind of boring and not something that a real cross-site scripter would use. So let's look at one more example, but focus on the script rather than the injection. In this example, we have a login page that allows us to switch the theme, very similar to our DOM-based example. The theme is stored as a query fragment, meaning it won't be sent to the servers, so this is going to be a DOM-based attack. We are going to create a basic keylogger. So we're going to spin up an attacker server. All this server is going to do is listen on port 4000 for information sent to it. Our script, which looks like this, is just going to record keyboard inputs and send them to port 4000, where our attacker server is listening. When we attach this script to the URL, it's going to look something like this. Now, all those funky characters with the percent signs and whatnot are just encoding special characters. URLs can only safely include a limited set of characters. So for characters outside that set, they use something called percent encoding, where you take the character's associated ASCII value, convert it to hex, and then put a percent sign in front of it. For example, %3c is equivalent to a less than sign, and %3e is equivalent to a greater than sign. If someone were to visit our malicious script and try to enter their username and password, those keystrokes would get sent to our attacker server. Now, it's important to note that when creating these examples, no security measures were put in place. In fact, there were decisions made to actively worsen the security for sake of example. So the last thing I want to do in this video is walk through a real-life cross-site scripting attack to demonstrate what cross-site scripting looks like in the real world. We're going to look at an example from 2017 that happened at eBay. Now, eBay allowed users to use active content in the description of their listings. Although they did filter this active content, since allowing users to write any JavaScript they wanted is a blatant security risk. But the filter that they used only stripped alphanumeric characters from inside the script tags. This means that you couldn't use any numbers or letters, so any of the examples that we've looked at today wouldn't work since all the characters would be stripped away. But the researchers who discovered this exploit used a technique called JS-fuck. Now, JS-fuck is an incredibly clever technique where attackers are able to write JavaScript with just a few characters, specifically these 6. Now, the mechanics behind this are pretty complex, but from a high level, attackers intelligently arrange these 6 characters so they're evaluated to things like false or undefined. They can then index these strings to get specific characters, and from these characters they can build entire scripts. A JS-fuck encoded script could look something like this. Now, to you and me, and to eBay's input sanitizer, this looks like gibberish. But the computer interprets all these characters as normal JavaScript. So attackers were able to trick the eBay input validation to allow JavaScript to be written in the listing descriptions. This is an example of stored cross-site scripting, since the item descriptions are stored in the eBay database and loaded when a user accesses the page. Once the attacker is able to execute JavaScript, they can do a couple of things. The first is a phishing style attack. The script provided in the listing description could call a larger script hosted somewhere else. The script would redirect the user to a different URL that hosts a cloned login page. So this would be a domain controlled by the attacker, but looks exactly like the normal eBay login page. But it would save and send the credentials to the attacker. Once a user enters their login information, they would be directed back to the normal eBay URL to a standard listing no longer available page. So in this attack, the attacker is able to steal your credentials and use your account to perpetuate the attack or to sell your information to other malicious parties. Another type of attack could be to use the malicious script to trick victims into downloading some type of malware. An alert type function could be used to pop a window up on the screen and ask the user to download some file, this file being some type of malware. But because it seems like this is coming from the official eBay site, users are more likely to trust it. If the user downloads this file, the floodgates are open, and the attacker can do any number of things depending on the specific type of malware used. This goes to show you how dangerous cross-site scripting can be and the type of doors it opens for attackers. It's also interesting to see how cross-site scripting can be used in conjunction with other techniques like phishing or malware distribution. So I hope you found this video informative and were able to learn something about cross-site scripting. As always, the code used in the demonstrations and animations in this video will be linked below along with the video bibliography. Until next time, thank you for watching.